Okay, here is another problem. This one has these two wheels that are meshing. They both have mass. It's a 1 degree of freedom because if you stop the top gear from turning, then because the other one it rolls with no slip, this one has to stop as well, so it's 1 degree of freedom. It happens to be first order because the only thing that can be stored in here is the kinetic energy. There's no potential energy because there are no springs. Okay, so what I've done here is drawn the free body diagram. This force P is a pressure that the two gears are being pressed against each other. And as one gear moves, there's going to be a tension or a gear teeth equation force, or parallel to that surface. They're equal and opposite. So if you notice, the P on one gear is up, the other one is down. One is right and one is left on the T. It doesn't really matter which direction you draw these because you're going to end up solving for them. Positive numbers mean that you've drawn them in the correct direction. Negatives mean that they've just flipped direction. So that's not a problem. There is a relationship between the motions of these gears. I like to, the way I teach dynamics is to say that these 2 points, A and B, are in temporary contact with each other with no slip. And that means that the velocities are equal to each other. The velocities of A and B are given by these formulas here, which is basically the omega R formula that comes out of dynamics. And so hopefully this kind of makes sense. So if, because of the way I've drawn the positives for the angles, if theta 1 is positive, theta 1 dot is positive, point A is moving to the right, and if theta 2 dot is positive, point B is also moving to the right. And that's why these equations have positives in front of each one. Okay, so normally I would save that to the last, but okay. All right, so now what I'm going to do is some moments on the gear 1. And this is the moment caused by the T. That's the force times its moment arm. It has a damper, which is C1. Maybe I should have talked about that. C1, a damper, the damping force is the constant times the speed. These are rotational dampers. If theta 1 dot is positive, then I am pulling or twisting the damper counterclockwise. If I pull it counterclockwise, it resists me and pulls me clockwise, and that's why I have the arrowhead in the direction that I have. Same thing with the C2 down here. It's got a damper times its speed. If theta 2 is positive, the way shown, then I am twisting this damper clockwise, and therefore it twists me counterclockwise, equal and opposite. So anyway, those are my forces, and then that's equal to the moment of inertia through the center of mass, and it's of body 1 because it's only the moment of inertia of the mass that's in the free body diagram. And then likewise I have the moment caused by the teeth force, or the force of meshing, the moment of the damper, because it's a rotational damper. It's not located on the rim or someplace else. It's actually a torsional one, so I don't have a moment arm on that. Equals its mass times acceleration. So if you count the number of unknowns, the unknowns happen to be theta 2, theta 1, and T. So there are 3 unknowns, and I have 3 equations, 1, 2, 3. So basically it's done, and then you can go into to to solve this if you want. So that's what I've done here. I've shown that you use one equation to solve for the t. Makes no difference which one really, and then you substitute that into the second equation, and off you go. So if you wanted to combine them all into one equation, it'd be easier if you just used Mathematica. But anyway, there you have it. If you want to turn it into a transfer function, remember you have to apply a external force. And so if you did something like that, then you might put in a say a moment here. We'll call it big M or something. There's a moment that will twist on the thing there, and since that's in this body number 1, that would go in right here. So it would be minus M goes in right there, and then you can use your transfer functions to